Okay, so yesterday we talked about exponential functions. We kind of introduced ourselves. We made a very straightforward, and if you recall, our exponential function was, it was start times change to the x power. And whatever we start with, like that's our patient 0 in our example about COVID. We change by doubling, tripling, halving, whatever, and we don't know how many times we're going to double, triple, halve, whatever. So that's why that's our exponent. That's why we're raising to the x power. This is how many times that change occurs. Okay, so like we talked about yesterday, rate of change in exponential is multiplicative. And that's what makes exponential functions different from linear and quadratic. So I want to really briefly talk to you about that, because a lot of times y'all once we get exponentials, y'all start to get linears confused. So let's think about this. How do I get from 5 to 7? If it's linear, I add 2. So I'm adding to get to the next row, okay? If it's quadratic, I add once. So I do my delta y. So this is my delta y. I do my delta y, but I have to do that again. So my delta y2, so my second difference. So I'm still adding, but for linear I add once, for quadratic I add twice. Well, exponential is, and then I will just, spoiler, for cubic you would add 3 times. Okay? So the power that it's raised to tells you how many differences you have to go out to find a common difference. Well, on this one we're finding a common ratio, and a ratio is multiplicative. So instead of adding 2 to get from row to row, I'm multiplying by 2. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So to get from row to row to row, we're multiplying instead of adding. Okay? So again, when we talk about exponential functions, the start value and the growth rate have to be greater than 0. And let's talk really quickly about why. So let's say we use that example of COVID, right? And I'm starting my COVID. So somebody has COVID. So I have one patient and they've got COVID. And their growth rate is 0. Okay. Okay, so after they're exposed to one person, there's no growth rate. Nobody can get it from them. Why are we even having this conversation? Because we're just going to multiply by 0 a bunch of times, and guess how many people are going to get COVID? 0. Okay? So if there's no growth or decay, then it's not exponential growth. It's not growth and decay if you don't actually have a growth rate. So it's got to be greater than 0. Also, it can't be negative, because like, what even is negative growth? I don't even know what that means. It's not decay, because decay is multiplying by something between 0 and 1, right? So it's not decay. It just doesn't make sense. Okay, now likewise, I have to have a start value of 0, because let's say I have nothing and I double it X number of times. Well, then I've got nothing. If I don't have something to grow, I can't grow it. So I have to have a growth rate bigger than 0, because otherwise I'm not growing. I have to have a start value bigger than 0, otherwise I have nothing to grow. So my start value and growth rate have to be bigger than 0. Okay, now my y values are going to approach 0 but never reach them. And we talked about this yesterday when we talked about how if I take a piece of paper and I cut it in half carefully, perfectly, and throw away half, I've got half left. Cut that in half, I've got half of that piece, and I have half and half and half and half and half. And theoretically, of course we know practically we're eventually going to hit an atom and then we're going to have a nuclear explosion. But from a theoretical perspective, I'm never going to stop running out of half of that tiny, tiny microscopic electron microscope sized piece of paper that I'm cutting in half. So I'm never going to reach 0. So I'm not going to, so what this means is, for now, no X-intercept. There's no X-intercept, because the line's getting closer and closer and closer and closer to 0, but it's never going to touch it. Now, if we see there are certain situations where we might see them. It's rare. I'll show you what they look like. But for now, for Algebra 1 exponential functions, we're not going to have x-intercepts. Now that value that it's approaching is called the horizontal asymptote. And what confuses y'all sometimes about the horizontal asymptote is, in this case, the horizontal asymptote is the x-axis, okay? So it's the x-axis, which has an equation of y equals 0, right? But you think, well, that can't be the asymptote because it touches it. It's the line that it looks like it blends into. So the asymptote, yes, it never touches that line, but our printer isn't a precise enough tool for us to be able to see that it actually isn't touching. It's getting closer and closer and closer and closer and never touching. So it's approaching the x-axis. And it looks like it's actually blending into it. Whatever line it looks like it's blending into, that is the asymptote. And it's spelled like that, asymptote, okay? We only have horizontal asymptotes because we're only approaching x, the x-axis. We're only approaching the x-axis, some y value. There are functions that have vertical asymptotes, but these aren't them, okay? So that's what we have about our old functions, so going back to it. So we're going to do 2 examples, and then we're going to do another one in class together. Okay, so first of all, it says the number of people attending a carnival doubles each year. The table represents the number of people attending annually. So it says they're doubling. So the first year they looked, only 30 people attended, okay? They doubled that. Well, on the next year, we had 60 people attend, okay? We doubled that, and we have 120 people. We double that, we have 240 people. We double that, we have 480 people, okay? So first of all, am I growing linear or exponential? Well, I'm growing exponential. It's nonlinear, and what it is it's exponential. And it's growing exponentially because I'm multiplying. Is it growing or decaying? Well, it's getting bigger, so it's growing. Okay? Now, this question I want you to think about this question, and we can talk about it a little bit tomorrow. Okay? Is it discrete or continuous? I could kind of see it both ways, but I personally think it's discrete. I want you to think about that question, and tomorrow I'm going to ask you about it. When you come in class, I'm going to be walking around the tables. I'm going to be asking you about that question, because I want to know what you think. Is it discrete or continuous? So we're going to save domain and range for later. Okay? We're going to save that actually for a couple days from now. Well, I think tomorrow? We're doing domain and range tomorrow? Tomorrow we do domain and range. Okay, so we're going to save that for Monday when we talk about domain and range. Okay, now, X-Intercept. What did we just say about when this thing's going to... Well, let's graph these points real quick. Let's just graph them. So I have 0 and 30, 1 and 60, 2 and 120, 3 and 240, and then I ran out of graph. Okay, now, in this situation, this kind of looks like half a parabola, but it's not. Because if it was half a parabola, I would be adding and then adding again. I'd be adding twice to get this value. I'm multiplying to get these values. That makes it exponential. So what that means is back here, there's actually a value there's kind of like invisible values getting closer and closer and closer to the x-axis, but they're not going to touch. And for that reason, my x-intercept is none. There is no x-intercept because it's never going to cross. It's getting closer and closer and closer. Okay? Now, y-intercept, as we talked about yesterday, is my start value. And it's right here in the table, and it's right there on the graph. And if they told me I had, a carnival with initial attendance of 30 people, that would be telling me what I start with is my y-intercept. So my y-intercept is 0, 30, which is also my initial amount. Okay? What am I growing by? My growth rate is 2 because I'm doubling. Okay? So now that I know my start and my growth, remember my equation, it's start times change to the x. Well, that's 30 times 2 to the x power. Okay? What is it approaching but will never touch? Well, it's approaching the x-axis, which has an equation of y equals 0. All right? All right, let's try another example here. Okay? This time we're using y equals 200 times 0.75 to fill in the graph. Now let's just pause for a real quick second. And of course I don't have any paper, but I want to talk about something here. So this first one, so our first equation was 30 times 2 to the x. This equation is 200 times 0.75 to the x. Okay? So let's keep that in the back of our head real quick, and let's get some values out of this calculator. Well, first of all, we have 0, 200, right? I have a value up there at 0, 200. Okay, so let's just use our calculator and figure out what the next point is. So let's put that in here. So 200 times 0.75 to the x power. And let's just look at the table. Okay, so after one round of whatever this is, I'm at 150. After 2 rounds, I'm at, oh yuck, 112.5. Oh, maybe right there. And then I'm at 80, okay, 80 something. And then let's see, let's just jump a little bit. When I'm at 8, I'm at about 20. Kind of see how our curve is starting to develop. At 10, I'm around a little above 10. So do you see how, like, if we were to trace that, we can see that our exponential curve, don't judge me, that our exponential curve is starting to develop. Okay? So there's our exponential curve developing. And so, like, we can just fill in those if you want to. We can fill in those values in our table, but I'm not really as worried about that. I'm more interested in what you guys seeing that this curve is developing. So is this growing or decaying? It's decaying, and it's nonlinear, and it's because it's exponential, because we have exponential decay. Okay? Now, what do you notice about this one? This one is growth, and this one is decay. What I notice is that this number is bigger than 1, and this number is between 0 and 1. Seriously, stop. Okay, it's between 0 and 1. Okay? So as I get closer to 0, like, so when I move from 1 and get closer to 0, I have decay. When I go from 1 and move away from 0, I have growth. Okay? I'm never going to have growth of 1. Because growth of 1, so like say, let's pretend that I have, let's just pretend I have 2 chickens, and I don't know, they're growing, they have a growth rate of 1. Well, what does that look like? Let's put that in the calculator. 2 times 1 to the x power. It's a straight line. It's not growing. You can't grow, like, a growth rate of 1 means no growth is occurring. Okay, so you can't have a growth rate of 1. It's either got to be bigger than 1 or it's got to be between 0 and 1. But it's not going to be 1. This is boo. Okay, and doesn't exist. Okay? So again, we're going to save domain and range for tomorrow. We'll talk about that. But you notice I connected the points. Do I have any information here to tell me whether I connect or don't connect? I have no useful information here. I don't know if this is about chickens. I don't know if this is about, you know, owls or bunnies or COVID or anything. I don't know anything about anything. So because of that, I have to say that it could be all real numbers. I have to say its range can be anything bigger than 0. I have to. I have no choice. And we'll talk more about this on Monday. Okay? So our X-Intercept, it's exponential. What's its X-Intercept? Its X-Intercept is none. It doesn't have an X-Intercept. Okay? What's its Y-Intercept? Well, its Y-Intercept is where we started, and and it's in the table, y'all. Its Y-Intercept is my A value, my initial value, my 0 row, my Y-intercept. It's 200. Well, it's 0, 200. My initial amount is 200. What am I growing by? Well, here's my growth rate, because it's start times change. Well, I'm changing by 0.75. So again, the equation they give me is, and the equation I can make from the data is 200 times 0.75 to the x. What is it approaching? Well, it's approaching the x-axis, which is y equals 0. All right? So that's all we're going to do for today. Tomorrow in class, we'll go over some more examples.